Okay, so in this one we'll solve problem F4-2. So we've done one similar to this. This is similar to the one we did in class. It's just maybe a little more involved. It's a tube with multiple sections. The ends are solid. The center is hollow, as shown here. And it's loaded as follows, and they want you to figure out the displacement of D with respect to A. So basically how much this whole thing extends or contracts. So again, the way you do this, we're going to use the axial extension equation PL over AE, but we have to break the problem up into the regions where you have basically constant loading conditions, right? So that equation, delta equals PL on AE, remember, that only works when the internal reaction normal force is constant through the element, and then the A and the E are also constant through the element. So that means, I'll do it, that basically we got to consider three separate sections here. Okay? So we have the section from A to B, B to C, and C to Z. C to D. Okay? And we can do PL over AE for all of these. Figure out the elongation or the compression of each section and then add them together. Okay? Let's zoom out. Too much. Okay, so this is problem F4-2. And basically, we'll do a crude drawing of the specimen. So this is A, B, C, and D. So these little flange plates here, I think we're safe to assume that we can, they're so thin that any elongation on those can be ignored. All right? So we have 10 kilonewtons that way, 20 kilonewtons on that end, 15 kilonewtons here and here, and then 10 kilonewtons here and here. Okay? It's kind of drawn a little small and sloppy today. I'll try to be a little neater on that one. Okay, let me just mention one thing real quick. So, when they draw these, they have these 15 kilonewton forces on the top and the bottom. Just to be clear, typically for engineering structures, kind of the way this stuff is actually done is as follows. You usually have what's called a bolt circle, okay? And usually have these flanges, and you'll have a circular pattern of bolts around the flange, okay? So in fact, I drew 6, there could be 8, there could be 4, it doesn't really matter, okay? And what's probably intended here is that actually there's a net force acting on this bolt circle. This is called a bolt head circle. All right, sometimes it's abbreviated BHC on that flange, and there's probably a net force of 30 kilonewtons, okay? Okay, so just to explain, that's typically the way these things are. They're not usually at 2 points, okay? I guess it could be a bolt pattern with 2 holes, but usually it's an array like that. The problem actually doesn't matter because we're assuming axial loading, so whether the forces are at 2 points top and bottom or they're in some bolt head circle pattern around the flange, it really doesn't matter. I guess I should put the little... Okay? All right. So again, in this problem, we're going to break it up and we're going to get the the elongation from A to D is equal to the elongation of section AB plus the elongation of section BC plus the elongation of section CD. We're all going to use this PL over AE, so I'm going to use the NAB. This means the internal reaction force in section AB times LAB over A from AB times E. I think it's all the same material. Where'd the paper? Yeah, I think it's all aluminum, okay? And then plus the internal reaction force in section BC, because that's constant through there, through the length BC, over the area of BC, that's the hollow cross-section, times Young's modulus, plus finally the internal reaction force axial in CD, the length of CD, cross-sectional area of CD, which is I think the same as AB, times E. That's the elongation. And now, again, we want to be careful about getting the correct signs on the ends. So this one especially, we need to be careful to make sure that we have the right sign convention. Positive means tension, and negative means compression. Okay? Why? Because if it's in tension, the delta CD has to be positive. So some of these might be in tension, some might be in compression. If you screw up the signs, the summation will be incorrect, obviously. Okay? All right. So now we just need to get the reaction forces, internal reaction forces. So that's relatively easy. Let's first do a section through AB. Let's do a cut there. Call that cut 1. So this will give me a free body diagram that kind of looks as follows. Okay, we know there's the 10 kilonewton force there. So here's the internal reaction force, NAB, and we always assume positive tension. So that gives me the force acting to the right. So that means when I do the sum of forces, I have 10 kilonewtons plus NAB equals 0. So that gives me NAB is minus 10 kilonewtons. So I'm taking it slow, but I want to make sure that I get the sign correct. Let's do the same thing for the second cut here. Let's go through BC. So that looks as follows. We have the 10 kilonewtons acting there. Here's the cut. So again, the internal reaction force is assumed positive in tension. So this is NBC. And we have forces at the flange, 10 kilonewtons, and then another 10 kilonewtons. So we do sum of forces here. We get 10 kilonewtons from this one, minus 20 kilonewtons. Just added these two together, plus NBC equals 0, and then that gives me NBC is in fact in tension of 10 kilonewtons, okay? So it's a positive 10 kilonewtons. And then finally, let's look at a cut here. That's section 3. We'll do it from the right side. Right, here's the 20 kilonewtons. Again, okay, so the internal reaction force we're assuming is positive in tension. So this is a negative face, so it's going to point in the negative direction, okay? So it's pointing always outward, tension positive. This is NCD. And then again, you do sum of forces, and you can see that this is actually in compression, and NCD is minus 20 kilonewtons, okay? So we're pretty much there. All we need to do is just do a little math on getting the cross-sectional areas, putting in the Young's modulus, and then we should be there, okay? All right. So let's just compute the areas really quick. All right. Well, we know that LAB is equal to 0.4 meters, and we know that LBC is equal to 0.4 meters, and we know that LCD is equal to 0.4 meters. They're all the same. The cross-sectional area in section AB equals the cross-sectional area in CD, and that is just going to be pi on 4. It's solid, and so its diameter is 0.02 meters squared. So that comes out to be 2 enter 0.000314 meters squared. And I'll put another digit on there for 2. All right. The area of BC, that's the hollow section. So that's just going to be pi on 4, the outer diameter squared, which is 0.04 meters squared minus the inner diameter, which is 0.03 meters squared. And that becomes 0.000549.8 meters squared. Okay? So those are the cross-sectional areas. It's aluminum, so Young's modulus for aluminum is, I should remember this now, right? It's the 27.9 gigapascals, right? I think that's it. 29.7 or 27.9? I can never remember. Oh, it's not even close. It's 73.1. 73.1, sorry. I should remember that. 73.1 gigapascals. Okay. Oops, sorry about that. I'm going off the screen. All right, so now we can put all that stuff together. So delta AB is equal to NAB, which is minus 10 kilonewtons times its length, which is 400 millimeters, over its cross-sectional area, which is 0.003142 meters squared, times Young's modulus, which is 73.1 times 10 to the 9th pascals, right? And when I do this calculation, the 10 to the 3rd of the kilonewtons cancel out with 10 to the minus 3rd of the millimeters. Put this up here. So that gives me 4,000 on top. Okay, so that gives me 1.741 times 10 to the minus 4th meters, which is 0.174 millimeters. Okay, we do the same things for the other sections. BC, and I gotta remember it's a negative, right? Don't drop the sign. That's the most important thing. That's the easiest thing to screw up. Forget the sign on that one. Delta BC is going to be its internal reaction force is a positive 10 kilonewtons. Its length is 400 millimeters. Its cross-sectional area is different. Its cross-sectional area is the 0.000548 meters squared, and then again, it's still 73.1 times 10 to the 9th pascals, okay? And so, actually, it's the same number as this, but just divided by the ratio of 0.003142 over 0.005498. So now I get an extension of 9.963 times 10 to the minus 5th meters. It's a little less because the cross-sectional area is bigger. It's got stiffer. And then that gives me in millimeters, that's 0.09963 millimeters. Okay, positive, it extends. And finally, let's do CD. So that is the axial force in CD. We figured out was minus 20 kilonewtons. Its length is again 400 millimeters. The cross-sectional area is the 0.0003142 meters squared, and it's the same 73.1 times 10 to the 9th pascals. So you can see it's just the same as this. It's actually just 20 instead of 10, so it's 2 times that. So it's going to give you a minus, let's just times that by 2, minus 0.348 millimeters. Okay? And then if we add those together, so total elongation from A to D is going to be minus 0.174 millimeters plus 0.09963 millimeters minus minus 0.348 millimeters, and that gives me minus 0.422 millimeters. Okay? And so that's the final answer.